Welcome everyone. My name's Anna Reinhardt. I'll be talking today about functions, call stacks, and call semantics. So basically what we're going to cover today is everything that relates to functions. And you've seen all sorts of things about variables before, and so you've also seen stacks before. And a call stack will turn out to be very, very similar to what you've discussed with stack memory allocation in the last session. So the first topic is functions. And the first question you can ask yourself is, what is a function, even? Okay, so if we're talking about a mathematical function, then we have a very clear idea of what that means. A function is something which maps some input variable to some output, and it needs to be unique, so we can't say that if we have a function f, that f of 2 is going to be 3 and 5. We have to pick one. But our computer functions the same way. If anyone is actually online, you're welcome to write in the chat and let me know if you know. So does a computer function work the same way? If I give it one input, do I always get the same output? Okay, so the answer with a computer function is no. So a function can output different things, even though you've put the same input in. The function in the computer sense is not like a function in the mathematical sense. There's some exceptions to this. So in some languages, functional languages, a function in the sense of that language is also a function in a mathematical sense. If you've ever programmed in R is a functional language in which that is the case. If you studied computer science, then you've maybe seen Haskell. Haskell is another example of a functional language. But C and C++ are not functional languages. They have some functional features, which I think you'll see next week, some of those. But in general, a C function doesn't have to be a mathematical function. It doesn't have to map an input into some output. So what does it mean then to be a function in our sense in C and C++? Well, we'll have a look at this definition. In computer programming, a function or subroutine is a sequence of program instructions that performs a specific task packaged as a unit. This unit can then be used in programs wherever that particular task should be performed. Functions may be defined within programs or separately in libraries that can be used by many programs. In different programming languages, a function may be called a routine, subprogram, subroutine, or procedure. In object-oriented programming, it may be called a method. So this gives you a very clear idea, hopefully, of what a function is in computer programming. It's basically just a way of encapsulating a particular idea so that you can reuse it. So any time that you have some calculation or some specific task and you think that you might want to do it several times, you should definitely put it in a function. But in many cases, we should also put these kinds of ideas and tasks in functions if we only want to use them once. And the reason for that is that it makes it much easier for a different programmer who comes into your program to understand that this is a single task, right? This is where it starts, this is where it ends. It makes your ideas separate out in an easier way and makes everything a lot easier. So how old do you think that the concept of a function is in computer programming? Again, not the concept of a function in the mathematical sense. Is it as old as computer programming? When Ada Lovelace, for example, was writing little algorithms, and she was writing them on a sheet of paper, actually, would she have used a function? The concept of a function is newer than that, so the first programming languages did not have functions. However, it's by our standards extremely old. So the use of subroutines, which we've seen are a different name that you could give to functions, were introduced in 1947. In 1952, there was the formal invention of the concept. So that's kind of when we would say is the birth of the concept of a function in this sense. And if you want to see how they fit into the different programming paradigms that you might have seen before, then this fits into structured programming according to Dijkstra. Okay, so the original first proposal for this is from 1947, but early programming languages did not have the ability to use functions. So let's do an example. We'll try to write a simple function, or rather we're going to first look at some code that doesn't use a function and see how that can go wrong, and then we'll rewrite that code and we'll use a function. So in this example, you want to make a down payment on a bicycle, and you're going to have to pay different exchange rates, and you're going to have to pay different exchange rates in different months. So this is a fairly complicated calculation for you to perform. And so you think to yourself, okay, I'm going to write some short code and I'm going to calculate what I'll need to pay each month to make this easier. And so you come up with this little C function. We'll go through everything line by line, even though a lot of these concepts you'll already have seen. So we're starting with an include of standard IO.h, which is the header file, which includes any input-output that we want to do. And we need that for printing output onto the screen at the end. And then we come to the main, which is always where our programs begin in C. So there always is exactly one main, and that's always where we start. So we have int main, and then we just start defining the different variables that we're going to need for our calculation. In this case, we have a double, which is the price of the bicycle. In this case, in this example, our bicycle costs 1,200. Well, I guess it's euros if we're buying the bicycle in the Netherlands. And now we've got different exchange rates, which are the exchange rates into pounds, for January and February. If on the first payment we pay 60% of the bicycle, then we again put this into a little variable, and now we want to compute the total cost that we'll end up paying for our bicycle, right? And you can already see some features of good programming practice in this. So you haven't just hard-coded those numbers in there, you've assigned them to variables at the start of your program, which means that if you want to buy a different bicycle in the next month, you can simply replace the price and you can replace the exchange rates, and then you can use the same program again, rather than putting all of those numbers into the formula underneath. But what we haven't done so far is use any function except for main. Right, so then we calculate our total price, and in this case we're just calculating the first payment times the price times the January exchange rate, and then the second payment times the price, and then the February exchange rate, and then we're going to print the total cost. So some of you may have noticed already that there's a bug in this code. So something is wrong, okay? Something is wrong. But we haven't noticed this yet. We just want to calculate our payments for the following month. And so we just extend our code and we calculate the cost for February as well by using a very similar formula. And what we've done here is something that we should never do. It's copy-paste programming. We've taken the chunk, which is the little formula we used for January, and we've just copy-pasted it down and then replaced January with February. And added March, of course, because for February we need then the following month. And what that also means is that because we had a bug in our initial code, we've now copy-pasted that bug down, and we've done it twice. So now it's just getting worse. And the more times you copy-paste something like this, the more likely you are to have bugs just flying around, because at some point you might go and you might say, oh, I see an issue in that line, and you fix it. But you don't notice that you've copy-pasted it somewhere else, and so the bug actually remains in your code. So what we'd like to do instead is we'd like to put in a function and avoid copying code. So we should take this calculation and we should encapsulate it in a function, and so avoid having these kinds of issues. So here's an example of a function. I've given it the very understandable name compute. So this is where we're computing our payment. And we'll already see a few things about the way functions work that we'll discuss in more detail a bit later. So it says void compute, and then it gets as an input a price, a first payment, a rate and A, and a rate B. And then it just copies that formula. And there's a small difference there. So if you look at this total cost in this example, you'll see a minor difference to the previous one, which is that the bug has been fixed. So it should actually be 1 minus the first payment. That is the second part of that formula, rather than 1 plus, right? So if you've paid 60% already, then 40% are remaining, not 140%, hopefully. And that then turns our code in main into just calls of this compute function. Right, so it's computing it for January, February, and then it's computing it for February and March. So we've discussed a few of the advantages of this already. So the first one is readability. So even when you're just calling it, writing cosine of 5 is much, much more readable than copy-pasting in some algorithm that computes cosine every time that you need a cosine. It's also much, much shorter. That's mainly the case if you're reusing functions. The second bit is maintainability. So when we want to change an algorithm, instead of changing the function, instead of changing it everywhere where we've copy-pasted it to, we now just need to change things once in that function. And if we want to replace a particular function with something else, so let's say if it was the example with the cosine and we found a more efficient algorithm that can compute it faster, we can simply go and we can replace our one function. We don't need to go everywhere where it's been used. And the third one is code reuse. So not in the sense of your own code, but if you've written a bunch of nice algorithms, you can now package up all of your functions as a library, and then you can provide them to other people. So duplicating code, it takes time, it introduces room for unnecessary bugs, and it's just not a good idea in general. So I think that this is not specific to C or to C++. You should try to write functions where it's appropriate, and you should really, really avoid ever copy-pasting code. So when you've got something and you feel the urge to copy-paste it, then something is wrong, and you should think, why do I want to copy this? Why do I not make it into a function? And there might be some reason for it, and there's probably a solution which still uses functions. So we'll discuss some reasons you might have for thinking, oh, I can't use a function for this, I have to copy-paste it, and we'll discuss the solutions. Okay, and as a last note, as a footnote, I've put down that, well, if you think about the example cosine 5, obviously you should not be implementing that yourself, right? So if the function has been implemented by someone else, is being provided by someone else's library, then it's good practice to use their implementation rather than writing your own. So this is especially true if it's just a standard, one of the C standard libraries that you just get whenever you use C. Okay, so let's go through C syntax. Something has gone wrong with my arrow here. I'm sorry about that. So the arrow should be pointing at the factorial here. So the function name in this example is factorial. And what this means is that when you're calling it, that's always the name you're going to use, right? So if I write a function, I write it like this: int factorial of int n, int result, and then I put in some calculation which calculates the factorial in this case, then I return result. The first bit there after the int factorial, that's always your function name. So the second thing that you write will always be the function name. You can't change the order of these things. You should always use descriptive names. So if your function is calculating a factorial, it should probably be called factorial. Usually function names are verbs which describe what that function does. You can't really make function names too long. I mean, sure, if they go over lines and lines and lines, they're probably too long. But if in order to be descriptive, you need to make the function name longer, then my tendency would be to do that. Because it just will make your life much easier when you go back into your code and you try to remember what the particular function was doing. Well, if the name already tells you everything the function does, then you're done, and you can still read your old code and understand it. And if someone else is reading your code, conversely, they can understand it. So try to give your functions names which describe it. Never give your names functions like f, like in mathematics. That's a bad idea. The next part is the return type. So the return type is the int at the start here. So again, my arrows seem to have drifted off, but the int at the start is the return type of this function. And the return type can be many things. So for example, it could be void if you don't want to return anything. And otherwise, it's just the type of whatever thing that you are returning. So it could be a double or an int or even some more complicated things that you've produced in the course of writing your program. So it can be a custom type. It doesn't have to be one of the standard ones. The next bit is our argument. So the argument here is int n. So that's everything which is in the brackets behind the function name. And you can have many arguments, so you don't need to have just one, as in this example. And an argument always consists of a type, in this case int, and a name of that variable, in this case n. And they fully specify what the inputs are to the function. So the function will get nothing else except for the things that you've listed here. A function can take one, none, or many arguments. So as many as you like, really. The order of the arguments matters. So when we're now running this code, obviously n is going to be n, but when you're calling it and you pass in different things, then the order, like the thing that you have named them at that point, does not matter. What matters is their order. So if I have int n and int m, then I can't say n is 3, m is 5, and then pass m, comma n, because they will end up in the wrong place inside of our function. So you need to recall what the order is that you've put on your arguments in the function. Next comes the function body. So the function body is this entire bit. So everything basically that's inside the curly braces. So from the opening of the curly braces up to the close of the curly braces is your function body. And your function body contains the actual implementation of the function. So this is where everything that the function is actually doing goes into the function body. Generally speaking, you should avoid making a function body very, very long. If you feel like you have to, then probably the task that you're doing is too complicated, and you should split it up into smaller tasks and write some more different functions that then maybe get called in this function. So generally try to avoid having functions which go over several pages, for example. If someone can't look at the entire function at a single time, they also can't keep it in their mind and comprehend what it's doing. So the entire point of this is to put in a little layer of abstraction that helps people to understand your code. And so you have to think, can a person who's looking at this, and this can be you, you know, like 2 weeks down the line, you've written this code, you look back at it, you try to understand what you've done, right? Can you keep everything in your mind that's going on if it's going on for several pages? The answer is probably not. So there must be little tasks in there that you could extract, that you can understand, that are smaller. So try to make function bodies fairly small. There's some exceptions to this where you might need much longer functions. But in general, if you can, keep the functions short. Next bit's the function signature. The function signature is the entire start here. So int factorial of int n is our function signature. And the function signature uniquely defines that function. So you can't have two functions with the same function signature. Okay, so you should not have another int factorial of int n. In C++, you can do something special, which is called overloading functions. In C, you can't do this. So what overloading functions means is that you can have multiple functions with the same name, but they have a different signature. So for example, you could have a factorial which returns a double and a factorial which returns an int. And they're two separate functions which calculate slightly different things. And in C++, that would be fine. So that's an example of an overloaded function. And in C, that's not fine. If you overload a function, then they still need to be unique. So you can't have two functions with double return types, but you could have one with int and one is double. So the compiler still needs to be able to tell which of the functions you meant to call. Otherwise, you can't overload it, basically. Okay. And the final bit is our return statement. So that's the return result at the bottom. And much like our start with the int, this can be void, and if it's void, then you don't need a return statement. You can only ever return a single statement, so you never can return multiple things. So we couldn't say, oh, I want to return result, and I also want to return I. You always return only a single thing. And yeah, if you don't want to return anything, you just don't. So if you have a void as your type, then just leave out the return statement. Some people then also just put a return with a semicolon at the end. That's also fine, but it's not needed. And the last thing is, while in this example the return result's at the very bottom, which is quite common, you can return at any point in the program. So I could put a return as the very first line there. And then what would happen is basically all the code after that would be ignored and never reached. But if I did that in an if statement, then that might make sense. So there's lots of reasons to put returns earlier in the function than at the end. So next, let's have a little chat about function scope. So we've already seen scope a lot of times in various ways. And so now let's just discuss it a bit so that we fully understand how that works. Because one of the most common mistakes I see people who are just starting out with C or C++ make is that they misunderstand scope and then their problem won't compile. We'll start with an example. And in this case, we're actually going to go and we're going to implement a cosine function. I've told you before that we shouldn't do this, but for some reason we want to write our own code to calculate the cosine. So perhaps your lecturer has told you that you need to do this. And so you think to yourself, well, I know the Taylor expansion of cosine, and I'm going to use that in order to calculate cosine and write my function. So the Taylor expansion of cosine is given below. It's just 1 minus x squared half plus x to the power 4 divided by 24 minus x to the power 6 divided by 720 plus and so on and so on and so on. And you can already see actually that we're using the factorial function in there somewhere. So the bottom bit there is a factorial. And in this case, we can just calculate our terms until we reach a precision. So if we want a cosine up to a given precision, we can just use this Taylor expansion and we can calculate it to that precision, regardless really of what that is. Bearing in mind, of course, the function type. So if this is a double, then we can never reach precision further than the double precision allows us to get to. And here's an example. You'll see by the way that I've titled it that, again, there's an error somewhere in here. And so you can start thinking about what it is, and maybe someone can write into the chat and tell me what the bug in this program is before I finished walking through what it's doing. But maybe not. Okay, So as usual, we start by including all of the libraries with other people's functions that we're going to need. In this case, we're including standard I/O, which again is containing things like print, so any input output. And then we also need math.h in this case in order to get some mathematical functions we otherwise wouldn't have. And the mathematical function in question here is actually the cosine, because I'm going to compare with the actually inbuilt cosine to check whether my implementation is doing the right thing. Okay. So we've used what we learned before, and so we're writing different functions. And you'll see one function here, which is called Taylor term, and it's just computing one of the terms in that Taylor expansion we saw on the last slide. It's getting an input x, which is the point at which we're evaluating our Taylor expansion, and it's getting a count, which is which entry in the Taylor expansion we're at. So which one, like are we looking at the second term, the third term, the fourth term, and so on. And so now we define a double step. We set it to 1. We calculate the Taylor step by multiplying our current step with minus x times x divided by 2 times count minus 1 times 2 times count. Okay, so far so good. Then we need to actually calculate the cosine, which means that we need to take all of those little Taylor terms and we need to sum them up somehow, right? So we'll start our count at 1. The first Taylor term will create a variable in which to store our result, which in this case is a double, and we'll set it to 1. And now we're going to see how far do we need to calculate. So we're having a while, and we're checking whether our value that we've calculated so far is more than 10 to the power of minus 3 away from the true result. So our result, so it's cosine of x, that's coming from the math.h, that's the kind of reference implementation. We're comparing to our result and we're checking, are we more precise than that? And if we are, then we stop. So then we calculate Taylor term, so we call Taylor term of x and our current count. Then we add the current step to our result, and then we increase count. And so we continue doing this up until we've reached our precision. Then we return the result, and in the main, we're just going to output whatever the cosine of 2.2 is in this case. So we're calling cosine of 2.2. Okay, can anyone tell me what's gone wrong here? So perhaps a more granular question first. Will this code compile? Any ideas? You're also free to copy-paste it into a compiler yourself and see if it compiles. So Taylor term does not have a return, it's a void. Exactly. So actually, we can't be using step here, right? So it makes no sense. It's not related to the step that we're using in cosine function. It's just not the same step. So even though we've named it the same, the program doesn't know. And the reason for that is scope. It's when is a variable in scope. If the scope of this thing went across the entire page, then there'd be no problem with this. Then the step in cosine would correspond to the step in Taylor term, and we could use it like this if we wanted to. So you've exactly figured it out. And now our question is, how do we fix it? You've actually also given me already the answer to that question, because you've said we should be returning something. That's the fix. That is one fix. So instead of just telling you one way of fixing this, I'm going to tell you 3 ways of fixing this code, which hopefully demonstrate a few different aspects of program scope. Okay, so basically functions define a scope due to their brackets. So those curly braces always indicate scope, and you can have curly braces all over the place, and you can even just place them with no other context. So if you want to restrict the scope of a particular variable to a particular area of your code, you can always just use the curly braces. It doesn't have to be around a function, it doesn't have to be around a while or an if or a for. You can just put curly braces and they will denote denote scope, and any variables you define inside those curly braces will exist only within that scope and not without. Okay. So variables of other scopes are not defined within our function. And again, we'll have a brief look at a definition. I think that this can be quite useful. And in this case, we're going to look directly at the C99 standard. So all of the C standards are available online, and you can read the entire bloody long document if you like, which nobody likes. But there's some parts of it which can be interesting to read at different points. So if something is unclear to you, well, everything is held down in the standard, and everything that C does or doesn't do is defined there. So a compiler basically just implements the standard. That's what it does. Okay, so an identifier can denote an object, a function, a tag, or a member of a structure, union, or enumeration, a type-def name, a label name, a macro name, or a macro parameter. The same identifier can denote different entities at different points in the program. For each different entity that an identifier designates, the identifier is visible, i.e. can be used, only within a region of program text called its scope. So the C99 standard very, very clearly tells us no matter what kind of a thing it is, whether this is a function or whether this is a structure or a union or an enumeration, all of which I think you've covered in the last few sessions, or if it's a type-def name, it doesn't matter, macro name, any of these things, if it's out of scope, it can't be used. Okay, so now let's look at different ways of solving this problem. My first solution actually does not use a return type, as you've suggested. That's going to be the second one we're looking at. Instead, this one uses something which is called a global variable. So instead of trying to return anything out of the Taylor type term, we're going to keep it a void, and we will define step outside of any function. So now it's at the very top there, right underneath our header files. Double step equals 1. And then below that, in the Taylor term, we do exactly what we did before. We just calculate the step by multiplying the previous step with this factor. And we use the same step inside the cosine, and we increment result by step. Okay, so has this fixed the issue? Yes, so the code is going to compile. Well, it did compile previously as well, but now the bug is also solved because the step inside our Taylor term is now actually the same step as in cosine. We declare step only once, so there's only one definition of the type of step, which is double, and we then use it in both of those different functions. So both C and C++ allow you to define global variables. Essentially what you see is that the step is not inside any of those curly braces, and so it's always in scope effectively. It's not defined in a particular scope, which means it's in a global scope. And we call any variable which is in global scope a global variable. In general, my advice would be to avoid global variables. So there's some reasons why you would use global variables. You should think about this carefully. This is because if you lose track of your global variables and then you think, oh, step would be a nice name for this variable, you're going to start running into issues. So if you do it very conscientiously. Think about whether you actually do need a global variable or whether there's an easier solution for your problem. Global scope is used in a lot of contexts. So for example, names of functions and names of other data types are, generally speaking, in global scope. In C++, names of classes would be in global scope as well. So there's some reasons to use global scope. There's a lot of reasons to define global variables. but in most cases, you should probably avoid using them. So let's look at a nicer solution for the problem. Let's look at the solution which you proposed. And that is much, much easier, actually. We just add a return type to our Taylor term function. So now, instead of having the function signature void Taylor term of double x int count, it actually has a double return type, and instead of defining step, we are now just returning that calculation that we did previously, and inside our cosine function we need to modify a bit now. So now we say step is equal to step times the Taylor term, so this multiplication which previously was in Taylor term is now inside that line of cosine, and then again we're summing up over all the different terms of our Taylor expansion as before. So this is a different way of fixing the problem. We just add a return type. Can anyone think of a third way of solving this, now that we've seen two? I've told you that I have three solutions. So none of these require a lot of changing of the code. This is going to be a very, very minor change. I'll show you one then. Instead of adding a return type, we can just add another argument. So we'll keep the void Taylor term, but now we'll just pass step in. And by passing it in, we're making sure that when cosine and Taylor term are talking about the variable step, they're talking about the same variable. So I've made this into a pointer. So step is now a pointer to step, and when I pass it inside the cosine function, you'll see that it has this lovely little and. So we're taking a reference and we're passing the address of step to the Taylor term function instead of step itself, and that allows the Taylor term to modify that value if it needs to, and then we can continue using the same code. So in a lot of ways, this is the same thing as doing the return type, but now our return is still void, and we've passed it in as an additional argument. Okay, and we're going to discuss the whole pointer and referencing and dereferencing thing a little bit more in the next section. Okay. So I said a little bit about function overloading before. I wanted to say a little bit more about it. So in C++, indeed, you can have multiple functions with the same name. In C, you can't do this, so there's no support for function overloading. Which is to say that if you take your C++ code, try to compile it with the C compiler, it's not going to work if it has function overloading in it. And yeah. So this is basically the same things I said before. Overloaded functions have different signatures so that the compiler can distinguish between them, and a function with multiple possible signatures is called overloaded. So there's a lot of reasons to use overloaded functions. If we think back about the example we just saw with the cosine, one reason might be that we need a much higher precision sometimes than we do other times, and so sometimes we want to pass in a float which has a very low precision, and sometimes maybe we want to pass in a long double and just have tons of precision to that and just run more and more Taylor terms. So then you might overload this function and allow it to have different return types with different precisions. Okay. So here's an example of a overloaded function in C++. So you'll note the difference here. This is called overload.cc because it's now not a C function. We usually, by convention at least, give it either the extension .cc or .cpp rather than .c. And again, because this is C++, instead of including standard I/O, we're now including I/O stream. So we're also including a different header here, which contains actually similar things, but not quite the same. So one thing I would also caution about that I see a fair amount with people programming is to mix up C and C++, because they cross-compile, right? So you can take your C code and you can compile it with the C++ compiler, and you can write some C++ features in there, but most of the code is C. If you can avoid it, I would avoid it. Try to write either C or C++. Just choose at the start. Pick whichever you like. C++ generally has more features than C, and then stick with it. And so that means that just because I'm showing you function overloading, I'm also going to show you what the C++ equivalent of certain functions are. So instead of a printf, we're now using these streams, so these I/O streams, which start with a standard cout, which is telling us that this is going to be outputted to our standard out. There's other options, so we could also put standard error there if we wanted to, and output it as an error message. And then it has these little, I never know what these little arrows are actually called. They have a name. In this case, they're denoting our stream, and so the integer is a string, which we're pushing into standard out. And then we're giving n, which is the integer in question, and then we're ending the line. And so this is a void. It takes as an input an integer n, and then we have a second function, which is also called print number, but this one takes a double, and it outputs the double is whatever we've input, with exactly the same syntax otherwise. And now below we have print number 2 and print number 2.0. And you'll see that I've here got an example where I've put in an int 2 and an example where I've put in a double 2.0. And it will then call the appropriate one of these two functions. Right, so it will tell what the type is of the thing that you've put in, and it will choose the appropriate function to print. So that's how function overloading works. And that's also part of the reason why you might want to do it. This allows you to just write print number whenever you want to print a number and not have to worry about it. The compiler will work out which of those two implementations you want. Okay, so some more C++ features that we haven't discussed so far. Default arguments. C does not support default arguments. If you've written a lot of code in Python, you've seen a lot of default arguments. Python allows these as well. If you're using an overloaded function, then you have to be a little bit careful about the order and where you put your default arguments. And you always have to put your default arguments last. So they can't be followed by arguments without default arguments. Again, if you've written a lot of Python, this will seem really familiar to you. And here's an example of default arguments. So we're again printing as before. We now have a program which is called default.cc because it's a C++ program. We're including IO stream, and we're sticking with our old function, which is print number. And it's now just passing two different inputs, a double and an integer, and outputting the double is this and the integer is this. And now we've used a default argument, so double x and then int a equals 2. So that means by default, if we don't tell it what a is, then a will be assumed to be 2. So it will always print the integer is 2 if we don't pass it an integer. And so for this overloaded function, this function's not overloaded. For this function, we can now call it in various different ways. We can call print number of 2.0, then it's going to print the double is 2 and the integer is 2, because it will fall back to the default. We haven't passed the default. We can also say print number 2.0, comma 4, and in this case, it's going to say the double is 2 and the integer is 4. So if we pass an argument, it will always take precedence over our default argument. And finally, I've written print number 2, comma 4. Does anyone have any idea what's going to happen with that one? So this particular function hasn't been overloaded, so I haven't written a version which is int. There's only this double int version. Is it going to compile? Okay, so this program is indeed going to compile, and actually in this case, it will just automatically convert that 2 into a double because it assumes you meant to call the only function which it could conceivably be, and because there's an automatic conversion from integer to double. So the corresponding double is obviously 2.0. It can make that conversion automatically. There are other types of conversions which can't happen automatically, where it doesn't know how do I convert from this data type to this other data type. And in those cases, your compiler would complain and this code would not compile. So in this case, it compiles, but only because there's an automatic conversion from int to double. So to reiterate that, if the arguments are matching exactly without any type conversion, then we're going to use that definition. If there is no exact match, but there is a match due to automatic type conversion, then C++ is going to use this definition. And this is a special case. We're not going to talk about const and non-const yet. But if there is a const and a non-const version of the argument, then C++ will use the const variant most cases. So this is something that's not specified in the standard, which means that different compilers can do this differently. But yes, in general, it's going to use the const variant if it can. In general, if you have the ability to make something const, you should. But this will be discussed later in the course. Okay, and with that we come to our next topic, and again I think I'm going to just take a very brief 5-minute break, and then we'll have a look at function declarations. Okay, so next we're going to talk about function declarations. So let's have a look at this example. So it's the same example that we've seen before with our cosine calculation. And I've really changed nothing except I've put the double Taylor term function with the return type at the bottom beneath the cosine. So I'll ask the same question that I've asked a few times. Maybe someone can answer it this time. Is this code going to compile? So previously it was compiling, and all I've done really is I've just moved this double Taylor term down. I've moved it below our cosine function. Will this compile? So feel free to just try it out, and you'll see. And what you'll see is that this code does not run. So the next question to ask yourself is why? Why doesn't this code run? And so what's going to happen as the compiler moves through this program? Well, it's going to start at the top. The include standard IO and the include math.h are essentially headers, which are simply copy pasting all of the code from standard IO and all of the code from math.h at the start of our program. That's essentially what they do. So you've maybe learned a bit about macros, and macros essentially just are kind of copy pastes into your code. And then it goes into this double cosine function, and it starts declaring the variables, count, step, result, all the variables that you've written down. Then it goes to the while. Everything is still fine, and then it gets to step equals step times Taylor term. And the compiler says, well, wait a second, I don't know what Taylor term means. I've never seen this thing before, because it's been going down the program from the start to the finish. And it's never seen Taylor term before. So it just stops and it says, I can't do anything with this. This is horrible, I hate it. And it throws an error message and says, I don't know what Taylor term is. You need to define it. So you always need to use your function you always need to declare your functions before you invoke them. So invoking them is when we call them. So Taylor term of x, count is the invocation of that function. And the function declaration, well, which part of that is the function declaration? It's actually only the bit where we specify the signature. The body of the function is not actually part of our function declaration. So we can declare a function just by saying double Taylor term of double x and count, int count. And then the compiler would be happy. It would go, so if it had that function declaration, it would go into cosine and it would say Taylor term, oh, this is a function which returns a double, and it takes a double and an integer. I've received a double and an integer. I can return a double here. Everything's fine. And so if we'd made that declaration, even if we haven't told it what Taylor term actually does or how it calculates anything, the compiler would be perfectly happy and it would continue going through your code. And then it would reach the double Taylor term part and work out, that's the implementation of this, and use it. So the only thing we need to remember is that we always need to declare functions before we invoke them. So one solution to this problem would be we just reorder our functions, right? We just move the Taylor term back up to where it was before, and we use it like this. So this is just the old code that we had before, and we've just moved our Taylor term back up. Okay, that's kind of nice, right? I mean, it works, and this is going to work for this problem because we have 2 functions in total, and that makes it really easy to work out which one should go first and which one should go second. However, once you have a lot of functions, reordering your functions would become extremely tedious. And even if not tedious, in some cases it could be impossible. So you could have some sort of a loop in there, which means that you need function C before function A, but you need function A before function B or something like this, which puts you in a situation where you actually can't reorder them in a way that makes the code still compile. So that means that actually we need a different solution. Instead of trying to reorder our functions to make sure that Taylor term is defined before cosine, what we should actually be doing is something else. And that something else is we should make a function declaration. So as I said, the function signature is actually the only thing that you need in order to define the function. So all the compiler needs to know is what is the return and what are the inputs, so that it can check that you've input the correct kind of things and that the output is the kind of thing that the program would expect. So in this case, if we've declared double Taylor term up there of double and int, the compiler, when you're calling Taylor term of x, count, can check is x a double, is count an int, and since they are, it's happy and it can continue. And it also knows then what step is, because we know the type of Taylor term. So it's a double times a double, which turns into a double. Yes? So in this case, the compiler stays happy, and we can place our actual implementation lower down. In this case, it's right beneath the cosine. So once we start doing function signatures and we just declare all our functions before we use them, suddenly we can reorder our functions any way we like. So however you want to have them ordered, you can order them that way, and they don't need to, you don't really need to think about the order at all. So we're not going to cover that in this session, but generally speaking, what you do in C is you create a so-called header file, which is separate from your implementation, and all of the declarations that you want to be usable by different parts of your program would go into that header file. So you'd have corresponding to ordering declare.c and ordering declare.h, and in those you would declare, for example, the Taylor term or the cosine. And the only functions that you should put into your header file as declarations are, again, the functions that you kind of want to be accessible from multiple files or in multiple places. So in this case, likely what we would want is actually to have only the declaration of cosine inside that header file, and to leave the Taylor term declaration inside this ordering declare.c. Why is that? It's because this Taylor term is actually a helper function for our cosine. It makes no sense outside of that context. No one should be calling Taylor term on its own outside of our cosine function, because it's actually not a function which calculates a generic Taylor term. It calculates the Taylor term specific to this particular cosine function. So if you have a header file, what you put in there is generally the things you want to be accessible from the outside. But the general kind of schema for any C project that you have is that you'll have a bunch of implementation files, which are called .c files, and then you'll have corresponding header files where you declare these functions so that you can use them anywhere. The exception for this is header-only libraries. So you'll note that math.h and standard.io.h are also header files, right? They have the .h ending. And so you could put the implementation directly into the header file if you want to just be able to include it like this. And if you want a library which doesn't need to be compiled, which people can just include as a header file, then you would put your implementation into the header file. Okay, so we've gone through this a few times. These are your kind of key takeaways, or the kind of best practices when it comes to functions. Really the main one, the only one, is one purpose, one function. A function should concentrate solely on one job. So if we look at the original definition of the word function, then it was saying this is something which performs a single task. So if you have a function, it should fulfill exactly one purpose. If you've done this, then probably you've already gotten quite a step towards the second point, which is avoid very long functions. If it's just doing a single job, it's unlikely to be very, very long. Document each function. This doesn't need to be extensive, so there's different styles in this regard. Different people have different preferences. I personally think documentation should be kept fairly short, but you should document what a function does. And your functions should have meaningful names. So in some cases, if your function has a meaningful name, you don't need any further documentation. If your function is called factorial and it computes a factorial, that's really all the documentation that anyone needs. But if your function is doing something much more complex, it's very, very useful to write at the start what your function is doing and document it. Okay. So since that bit was very short, I think I'll move directly on into call semantics. So when we make a function call, then we have to always think about two aspects of this: data and control. So I'll put both of them up already. Data is exactly what the word kind of says. What kind of data do we need inside our function? Where is the memory? How are we moving our data? Things like that. So this means things like the arguments of our function call, because they generally have to be moved in some way. Usually you do this by writing into memory mapped registers. And the results of the function, same thing, right? So we retrieve them by reading from memory mapped registers when we are getting back something from a function. So this is data. So if we have double factorial of int n, we are receiving back a double, and that is concerned with the data, right? And we're inputting an int, and again, the concern there is the data. But the second aspect is control. So if we're thinking about a function does particular operations in a particular order. And that order is usually really, really relevant. If we scrambled up our function and just did the things in a different order, the result would be really, really different. And so there must be something which is controlling that the sequence of operations that we want is actually being maintained. Right? So we're going to discuss control a little bit more in the next section. First, we're going to talk about data, which is probably the way that you've been used to thinking about functions is actually primarily about control and not primarily about data. Usually we think about data when we think about variables or we think about classes, but your function also contains data, right? So let's have a look at an example, and we'll do the same kind of a thing that we did before with the other functions. So I always show you code which has issues, yes? And so some of you are already looking, and hopefully you can find what the problem with this is before I finish describing what it's doing. So this is a very common example. We want to swap two variables. We want to turn A into B and B into A. As usual, we start by including standard I/O. Then we write our function void swap. It receives two input arguments, an integer A and an integer B. It has no return. It's defining a helper in which to store the value of A. It then assigns A to be B and B to be the helper, which is the original A. So now A has the value of B and B has the value of A from the start. So this swap function has swapped those two values in some sense. And so now we go into the main and we invoke that function. So we're going to define int A equals 1, B equals 2, and we're going to swap A comma B. What's going to be the output of that code? Yes, the return is going to be 1 comma 2. So indeed, they won't have been swapped. Does anyone know why they're not swapped? Pass by value. Yes, exactly. So some of you know a lot more about C already. Okay, great. So yes, so the problem is, in some sense, if we're thinking about data and we're thinking about a function, the problem is that when we pass in A comma B into the swap function, what we're actually doing is we're creating a copy of A and B, and then we're operating on them. So these are not the same A comma B that you had down there. They're the same symbols, yes, but they're not the same variables. They're not pointing at the same place in memory. And so that means that while if we put that print statement into the swap function itself, A and B would be swapped. Once we come back out, A and B are just unchanged. So we've operated on a copy of A and B, we've swapped them around. That doesn't help us with the original A and B at all in any way. Okay, so I'm not going to show you an example. So this is the one case where I won't go through different variants of fixing this code. Instead, you can do an exercise this afternoon and you can fix it yourself. We already know several different ways of doing this, yes? And as someone has correctly pointed out, the reason why this doesn't work is because in C and C++, parameters or input arguments are by default passed as call by value. And what does that mean? It means that you really are creating a copy of that variable. So what about Python or other languages that you know? So let's think about Python. I think a lot of people learn Python as one of their first languages. Does Python pass call by value? Does anyone know whether this, so if we rewrote this code, we rewrote it in Python, would it work? Okay, yeah, we'll go through a little bit more what the difference is in a second. But essentially, in a call by value, the value of A and B are being passed rather than their memory locations, which means effectively that we have a copy of A and B rather than having A and B themselves. So we can't change them, right? So unless we have a return in this, we can't change what A and B are. So A is 1, we're calling by value. So we're just putting 1 into the swap function. So again, in Python, would you expect for this to work? Does Python do call by value? Python, by default, uses something which is called call by reference, not call by value. And that means that in Python, this code would work. It would actually swap your functions. It also means that in Python, calling a function, like with swap a, b, can be dangerous. Because maybe you actually wanted a to stay 1 and b to stay 2. And now some other function's going around modifying it. And you never even wanted that. So both of these, call by value and call by references, can have pros and cons. You need to know what the language you're doing does by default. And in most languages, you can do both. So in Python as well, you can do call by value explicitly, but the default will be call by reference. So functions in call by value are going to work as copies of our original variables. And the original variables are basically saved away on the call stack and cannot be modified by the current function. To connect this to what we did before, those variables are no longer in scope. They're in their own little curly braces, and that means we can't access them from inside the swap function. It makes sense. Why would we be able to modify them, right? So with the stuff we've learned about scope, it makes perfect sense that this would not work. So I want to look at an example that we're actually going to solve rather than the swap, which you're going to do yourself. So we'll look at a different example, in this case an increment function. And in this case, it's got exactly the same bug in it that our swap function had in it, because we want to try to solve the same kind of a problem. So this is an increment function. It's supposed to increment a. So it gets some integer a. It sets a to be equal to a plus 1. And then it will print what the current value of a is, just so we can see what it is inside the function. And in the main, we're going to define an integer q, which is 3. We're going to increment it, and then we're going to print q. Does anyone want to tell me what this is going to print out? So it's going to print out 2 numbers. First one from inside the increment function, and then this printf in the bottom of main. So this is going to print 4, 3, because the increment function has exactly the same problem as the swap function. It's being called by value. So in this case, the value of q is 3. We're passing that in to the increment function. So this a variable, I've now named it something else, is 3. 3 plus 1 is equal to 4. It prints that. Then it comes right back out. But we haven't changed q, have we? So q is still 3, and we print 3. So this is exactly the same problem. I've also written a footnote for stating the obvious, which is don't write a increment function. Please don't. Okay, so this is the same problem we had. And it's also a problem that we've also seen multiple solutions for already. So one solution would be to add a return type to this. So if we would just return an integer and then return a as well, then obviously we could pass back out the data. So right now we're kind of passing in the data. We're not passing it back out. Or we could try to say, maybe we don't want to do call by value. Maybe we'd prefer to do something else. So this is the first solution with the return. We keep all of the code the same. The only difference is we've now changed the function signature, so we've added an integer to our return type. So now it's int increment rather than void increment, and we're returning a. And then we need to assign that, so here q is equal to increment of q. And in this modified code, we'll output 4 and 4, as one might think one should have. So in this case, the return statement takes the value of the function's copy, writes it to the left-hand side of the function invocation. And this works in this particular case, but it can't work for the swap function, because in the swap function, we had int a and int b, and we wanted to change them both. And we've already learned that we can only ever have a single return value. Yes? So There is obviously hacky workarounds to this, so we could return an array which contains A and B, but this is a horrible idea, okay? So we should try to just not try to write weird hacky workarounds to things. We should take them as they are. And in C, there's very, very clear ways that you're intended to write code, and you should only have a single return type, return value. Okay, so I said that in Python we do call by reference. I haven't said what reference is. And part of the reason why I haven't said this is because C actually doesn't have call by reference. C++ does. So in C++, the AND operator is the reference operator. And if you pass any variable with this AND, then you're actually passing it as call by reference. And this means that you're actually operating on the original data and you can change it. So if you were writing this code in C++ with a swap, you could just introduce some ANDs and you could do call by reference and everything would be magically fixed. So the main difference here, call by value and call by reference, is whether or not you're creating a copy or whether you're working on the original variable. I've told you that C doesn't have references, and as such it also doesn't have call by reference. And so now maybe when you've seen this AND symbol, you're now thinking, oh no, you're definitely wrong. I've seen this AND symbol used in C. And actually, the AND symbol in C means something slightly different than it does in C++, just to confuse you. So when you use this AND in C, and if you're using it in C++, it actually has slightly different meanings. There's no references in C. So we'll look at an example. And we'll look at an example in C++, so we're going to do some call by reference. So now you see all I've done is I've added this little AND symbol there. So now it's void increment int and A. So I'm saying this integer is call by reference and not call by value. And so now if I call this, what will happen is that I'm again going to output 4, 4. Because now instead of creating a copy of Q, I'm actually operating on the original Q, which means that when I get to the second print statement, the Q will be modified. It will be incremented. So here, the AND operator is our reference operator, and it tells C++ that we want to do call by reference semantics. And that in turn means that C++ does not create a copy, but actually operates on the original variable. And so you've seen something in C which is quite similar to this, like a way of operating on the original data. Can anyone tell me what the C variant of this is, what it's called? Or potentially what the kind of input argument of our function should look like if it was in C, instead of this int and. So if we were doing this in C, we'd want to have a little star. And the star is telling us about pointers. And I know that you've done pointers, and I also know that whenever anyone is learning C for the first time, pointers is the worst bit. So here's the corresponding code in C. So again, we're including standard io.h. And now our increment function looks almost the same, but instead of having this little and, which was the call by reference, we now have a little star. And the little star means that this is a pointer. And what's a pointer? Well, it points from your variable to its memory location. And so if you like to think about it like that, it's telling you the address of A. Where does A live? Where is that memory? Which means that if we want to increment it, we need to actually get the actual value of A. Rather than its address, because otherwise what we'd be incrementing is its address, and what we'd be returning would be the next address in memory. So if we did A equals A plus 1, we'd actually just be incrementing the memory location rather than its value. So this is why we need to have the little stars again. If you've never seen pointers before and this is your first time in the course seeing the pointers, I understand that the first time you see them, they are a bit confusing. I would just recommend doing a few exercises where you use them, and then I think they'll become quite clear. Because essentially you can just think about this as, well, what is a variable in terms of like in the computer? Well, it's essentially a memory location, and then what's actually written into that memory location. So it's a value and it's an address, and the pointer just gives you a way of accessing both the address or the value of that object, right? So that's the only thing that the pointer is doing. Okay, so this is the way of fixing the increment function in C. We don't have references, but we can still modify the value of a variable by using a pointer. And this is actually passed by value semantics. Okay? So we're passing the address of Q and creating a copy of that and then operating on it. But since the memory location is a fixed memory location, we can now change what memory is written at that point. And this is what makes C such a dangerous language, okay? You can write a function and you can change memory anywhere in the program. It does not have to be memory that is actually in scope, right? So your variables need to be in scope, otherwise you can't access them. But if I told you there's an int q, and then there's an int p, and I define it right after int q inside the main, with pointers in the increment function, even though I've only been given q, I can just say, oh, well, I know what's in the next memory location, it's p, and I can go and fetch it. Which means that functions don't necessarily need to respect scope. So you really need to watch out for this. If you've ever had a look at the way that people write obfuscated code on purpose, where they're trying to trick people into thinking that code does a particular thing when it doesn't, then they often use this kind of pointer arithmetic to trick you into thinking that a function is modifying only a particular area of the memory, but actually it's modifying something completely different. So this can lead to horrible, horrible bugs. It can lead to a lot of types of security issues as well. In general, it's just quite dangerous. So you should avoid doing these things, but it's a possibility in C. Okay? So we can pass the address, we can change whatever memory is written at that address. In theory, we can go and we can look at any memory anywhere in the program if we know where it is. So the next thing is, how do we actually return multiple values? Well, we can use the same thing, right? So if we want to have multiple values, here is an example where we're doing a divide function, and we actually want to return the result of our integer division, but we also want to return the remainder. So then one way of doing that is to say the result of our division operation is our actual return. So in this case, int divide, that's our return type, and it's returning numerator divided by denominator. So it's returning our integer division. But since we also want the remainder, well, what can we do? We can just pass the remainder in as a pointer, and now when we assign numerator, does anyone know what this percent means? I don't think I've explained the percent yet. Does anyone know what this little percent symbol means? It's a modulo operation. So we're just assigning the remainder into this variable called rem for remainder. And so if we run this code, so our numerator is 12, we're dividing 12 by 5. If we do this integer division, then what's going to happen? Well, 12 divided by 5 in integer division is 2, and the remainder will also be 2, and so that's what the program is going to tell us. So this is one way of returning multiple values. And a lot of people who write very classical old school C will actually make every single function they write a void type, so they won't ever return things. They will put all of their return types as pointers. And so the way that you would then look through the function signature to see what's an input and what's an output is by checking which things are pointers and which things are not pointers. If they're pointers, they're outputs. If they don't not, then they're inputs. And it allows you to have things which are both inputs and outputs as well. So that things which you want to pass in and then modify, like we did with the increment. So this is the way that we overcome this limitation in a nicer way than trying to write weird structures to encompass all of the variables we want to return. So the next thing was call stacks. So let's think a little bit about call stacks. Checking the time. So let's, again, we'll take just a very brief break, and then we'll continue. So you know this picture because you've seen this on day 2. So you know all about memory organization, about a stack and a heap and static data and heap data and kind of dynamic allocation and static allocation. You know all of this stuff, right? And I said we're going to think about data, and we're going to think about data in the context of functions. When you've thought about the stack and the heap before, and the static data, and so on, then you've probably thought about this in the context of variables, not in the context of functions. So you'll just recall very briefly that the stack is memory which has a fixed size at the beginning of our program. If we allocate things on the stack, they're fast, they're scope explicit, and they are managed by our compiler and our operating system. This is versus the heap, which has a flexible size, which changes during the runtime. It has, as a result, slower allocations. It's managed exclusively with pointers if we're talking about C. And allocation and deallocation are programmer responsibilities, which is to say that if you create an array on the heap with a dynamic size, then you allocate it with malloc, for example, and you need to deallocate as well. And it's your responsibility. And if you don't do this, you get memory leaks, and then everything is horrible. Functions operate exactly in the same structure. And in particular, function calls are kind of put onto what's called a call stack, which manages the order in which function calls are handled. And so this is the control aspect of functions that we saw before. So not the data aspect, but the control aspect. Which order do things happen in? And the call stack is, again, maintained by the operating system. It's a dynamic data structure, so it changes as you're walking through your program. And it uses a last in, first out mechanism. So if you think about the stack like a stack of papers, you've got a big stack of papers, you put one paper on top, that's the first paper you're going to take out. The last one that you put in, not the first one you put in. If we're thinking about threading, if we're thinking about parallelism, you will have a separate call stack for each thread if you do this. We're not going to discuss this in any detail in this particular course. If we're thinking about this, thinking back to the very first day in the von Neumann paradigm, then data and instruction stream reside in the same memory. So that means that call stacks and kind of the stack on which we allocate memory are the same thing. Yes? So data and instructions are the same kind of a thing in the von Neumann paradigm. And this is different from our Harvard machine. So let's walk through a call stack. I have here a really simple program. It doesn't really do anything at all. All it contains is a bunch of functions which are calling each other. And in order to tell you that they're not really doing anything, I've named them foo and bar. So they're basically just placeholder names and their placeholder functions, just to understand how stuff gets put on the call stack and how it gets returned off the call stack. So what we've got is we've got a function void bar, which just returns, so it just doesn't do anything. We've got a function void foo, which calls bar and then just returns. Again, it returns nothing, yes? And we have our main function, which just calls foo, and then it returns 0. So any program in C will start in main. Any program in C will have precisely one main function. If you try to write more than one main function or less than one main function, your program in C will not compile. And main is always, always, always your entry point into the program. So the very first thing that ever happens on the call stack is going to be main. The program always starts there. So now what's going to happen as we run through this program? Well, the next thing that's going to happen is we're going to call foo. So foo gets added to the call stack. So this is our little stack. You imagine a stack of papers. We're just stacking our functions onto the call stack. And what's foo going to do? Well, foo calls bar. So bar gets added to our call stack. And now our call stack contains bar, foo, and main. And if we want to remove anything from the call stack, so if we want to get it out of memory again, we have to go back down the stack. So we can't go directly and pull main out from the bottom there. Even though with a stack of papers, if you're willing to have them fall over, I guess you might be able to try to do that. But as we're kind of exiting, bar returns, we remove it from the top of the stack. Foo returns, we remove it from the top of the stack. Main returns, we remove it from the stack. Our stack is empty. The program is done. Okay, so that's the basic way in which the call stack works. If you have a more complicated program, obviously this will look a little bit more complicated. You can have all sorts of if-else complications and branches and all sorts of things in your program, of course, but the basic idea is you stack things up on top of each other, and then as you return, they get removed from the call stack again. There's 3 basic operations that you perform on the stack. You can push, so you can insert an element at the top of the stack. You can pop to delete the top element of the stack. And you can also peek, which is not something that we've looked at now, which just looks at the top element without doing anything with it. So this is the same kind of visualizing the same control flow that we saw on the last slide. We're starting in main, which means that we're pushing main to the call stack, then we're pushing foo to the call stack, then we're pushing bar to the call stack, and then we're popping first bar, then foo, then main off of the call stack again. So this is what happens anytime you're running any program, really. So if you have a serial program, not a parallel program, then you only ever have one function active at any given time, and that function is the function which is at the top of the call stack. So you never can look at anything which is not at the top of the call stack. Pushing and popping, again, always only happen at the top of the stack. So you really do think about the physical papers, and if you think that your stack is actually very, very tall, then even with the papers you wouldn't be able to pull out like stuff from the middle without disturbing everything. So this is the same thing. We push and pop only at the top. Obviously, memory in a computer is a finite resource. You only have a certain amount of memory. How much that is depends on your computer. And that means that if you have too many functions which are called before return, then the program can run out of space on the stack. And when that happens, this is called stack overflow. And usually stack overflow happens if you've written a recursive function that isn't terminating. Because then the recursive function keeps putting itself on the top of the call stack. And if we kind of think again back to the call by value, what's actually happening there is, well, we're creating a copy of that function, putting it on the top of the call stack. So once you get too many of those functions on top of the call stack, you get stack overflow. You run out of memory on the stack. Theoretically, you might also have a program which is simply so large that it causes a stack overflow. But I think the only place I've ever seen it happen in my own programs has been if I've mucked up something in a recursive function. Okay, so let's think back to the two aspects, data and control. We've discussed control, when do things happen. We've discussed a little bit about data. We've discussed about semantics of data, actually. And now let's think about the call stack, and let's think about data. Whenever you call a function, a new stack frame is created with all of the function's data, okay? And that stack frame gets pushed to the top of the program stack. And that is kind of associated with a bunch of data. So let's think about how this is going to move through memory. And in this example, I'm just going to start at memory address 2048. That's completely arbitrary, right? It's completely arbitrary. I've just chosen 2048. The start is arbitrary, but everything after that is built based on this last in, first out principle, which means that it's completely deterministic. We know exactly where things on the stack are. And so the starting address is something which will change. So if you run the same program multiple times, your starting memory address may change, depending. But after that, everything will be deterministic. So let's look at an example, and we'll try to walk through the function, and we'll try to work out where everything stays in memory. So here's the example. This example is now a little bit more complicated because we've added in some actual calculations again, but it's still a fairly simple little program. So we've got two functions in this program. We've got an int add, which takes a and b, and it calculates a plus b, assigns it to a new variable h, and then returns h. We've also got a function which is called multiply add, which takes three integers, a, b, and c, and then it calculates b times c, and then adds the result a comma h. So h is b times c, and then we add a comma h, which means that we are doing a plus b times c. So we're doing a multiply add. If you've done a little bit of high-performance computing already, then the multiply add will seem very familiar to you, because in a lot of hardware, this is actually hard-coded, and the multiply add is its own operation, which means you should never do this, because then it can't be optimized. Okay, so in the main, we are assigning a to be 1, and now we're trying to calculate the result of multiply add of a plus 1, a plus 2. Then we're assigning b to be 2, because why not? It's not doing anything. Then we're returning. And so now let's think about the call stack. And what we know is the first thing that happens, we go into main, and the main gets added to our call stack. And so now main gets its own stack frame, and that stack frame contains the variables that we're declaring in main. In this case, it's the variable a, which is an integer, and because I've arbitrarily decided that that's where we're starting, the variable a is now at address 2048. That was our start. So that's where a now lives. And the next thing that's going to happen in the main is that we call multiply add. And when we call multiply add, what happens is that multiply add gets added to the top of the call stack. And multiply add has its own stack frame, so it has its own memory addresses. And so now we have to remember that this is by default call by value. And so that means that we're going to create a copy of a And that means that the A that's being used inside this multiply add actually has an address which is higher than the address of the original A in the main. So it's at 2052. Can anyone tell me why it's at 2052 and not 2049, for example? So A is an int, and integers have 4 bytes, and so the next address in this case will be at 2052. If this was a double, that would be different. So A has a particular value, and it has an address. In this case, the address, once we're in multiply add, is 2052. The value that we've passed in here for A, B, and C are 1, 2, and 3 respectively, because A in main, if you remember, was A equals 1, and then we're passing A plus 1, and A plus 2. So 1, 2, and 3. And they are just added to the stack consecutively. In this case, 2052, 2056, and 2060 are their locations. H is written to the next open memory address, which in this case is 2064, and the value of it is B times C. And since B times C is 6, the value there should be 6. So what happens next? Well, next, the multiply add function is calling add A, H. And so again, we're adding a new thing on top of the call stack, and that thing is the add function, and that function again gets its own stack frame, and it gets its own copies of the variables. So the last variable that we defined in multiply add, and currently everything else is still on the call stack, so all of these memory locations are still in use, is 2068, so exactly 4 on from 2064, and we have again a new copy of A, a new copy of B, and again they're at 2068, 2072, and when we calculate this helper integer H, then the value of H, which is 1 A plus B, which would be 7 if we'd calculated things correctly, is put to the next memory location, which is 2076. So that was kind of building up the call stack. And so now what's going to happen? Well, we're going to start returning, which means we're going to start popping things off of our call stack. So what does that imply for our memory addresses? At first, absolutely nothing. We return out of both of those functions. So we return out of add, and then we immediately return out of the multiply add as well, because we'd called the add inside its return. And then we print those results. And now we're making an integer b. And where can we write integer b? Well, now that everything else has been removed from the call stack, we can actually write it onto the next address that's available, and that's 2052. So B doesn't go to 2080, which is where it would be if the other stuff was still on the call stack. It goes back to 2052, because now everything else has been removed. And so in this way, your memory gets managed. Okay, so if you call something and the other stuff has already completely returned, it gets removed off the stack, it's completely fine, and that memory will be overwritten. So if we think about what is actually program memory, well, the function call stack is in our program memory. There's a heap for dynamic memory allocation, and then there's some static data. So this includes things like global variables, which we discussed briefly. It includes things like instructions for running the program, which are not usually changed during execution. And the stack frame, which I kept referencing now, and I hadn't actually defined, the stack frame is the portion of the memory call stack which is associated with a single running function. So each time I called a new function and I showed you a little segment with the corresponding pieces of data on there, then that bit was a stack frame. Functions have many different inputs and local variables, and in that case they will also have large stack frames, and the compiler will determine the stack frame size for each function a priori, so before you run. There are as many stack frames on the call stack as there are active functions. So if you have a bunch of functions, none of which have returned yet, then you've got a bunch of different stack frames all on top of each other. And if you're calling recursive functions, then that can be the same function many, many times. So when we call a function, then we push that function onto the call stack, and when a function finishes executing, then we return control to the function that invoked it, and the frame of the returning function is removed from the top of the stack. So if we look back at our example, then in this example, because of the way we've returned add of a comma h, we're actually kind of exiting both of those functions more or less at the same time. So once add returns, multiply add also returns, and they both kind of drop off the stack at the same time. Right, I have only this very short bit left, so you can, while I want to talk about this mainly for completeness, you're generally not going to use function pointers, you probably shouldn't, but I thought it might be good to have that as a segment anyway. So we can point at data, and we've just kind of learned that a function is more or less just data, right? So the start of a function is just the start of its memory location, which is an address in memory. So logically, it kind of follows that we could have a pointer to a function. So here's an example where we have a function, void function int a. It just prints something. It doesn't have a return type because it's void. Now I have some rather cryptic code down there where I am saying void, and then I'm saying, pointer, function pointer, fun pointer of int. So I'm making a declaration there. I'm saying this is a function pointer, and it takes an integer. And then I'm assigning that function pointer to the address of the function. So I say and function, and this is C. So this and is not a reference, it's a address. Fun pointer is equal and function. And now I can use this function pointer. Instead of calling the function, I take star func pointer, so I'm taking the value of the function pointer rather than its address, which is what the pointer is naturally, and I'm passing it 10, which is an integer, and then I'm calling. So this is a little bit of a cryptic way of doing things, but it's possible. So it's possible to take pointers of functions. We can just call the function pointer rather than the function, and it follows all the usual rules that you're used to for pointers and pointer arithmetic. We need to have this particular bracket, because if we didn't have that bracket, this would look like a function declaration to the compiler. So if you want to write something like this, you actually do need those first brackets, which seem like they might not be needed. But yeah, so this is a function pointer. It's a thing that you can do. But where does a function pointer point? And what is a function pointer? Well, yeah, as with all other kinds of pointer, the function pointer just points at the start of the memory location. And in this case, that's the start of the function call stack. So basically, all that the function pointer is saying this is where this function starts. Same thing as when you have a pointer to an array, you're just saying this is where this array starts. You can play around a lot with pointer arithmetic in order to read out variables in the scope of other functions if you understand your call stack. Obviously this is dangerous, but I would recommend doing it at least once just to see what you can do with that. And function pointers can allow you to play around with that in some interesting ways. So if you think back about the example that we kind of walked through, where is everything in memory? Well, this implies that if you know that, then at any given point in the program, you can kind of inject in there and take out things or change things. And now especially if you're thinking about having multiple active threads, you can think about causing quite a lot of havoc if you want. And I think it can be quite fun. So if you use these function pointers, you can do another fun thing, which if you are inclined to do that kind of a thing, is a fun exercise, which is that you can implement classes in C by in kind of expanding our standard structures with methods by having function pointers in them, which basically define methods and turn our structure from a structure into a class. Obviously, this is an absolutely horrible way of implementing object-oriented programming. I wouldn't want to imply that this is a sensible thing to do, but it can be a fun exercise, and it will teach you a lot about how pointers work, how classes work, how structures work, and so on. In general, I would say, if you want a class, use C++. Okay. So that was the end of what I had. Thank you all for listening. And